Hi all, I welcome you to the discussions of alcohols and phenols once again. We were talking about various aspects of alcohols and phenols the other day. We were looking into the physical properties and chemical properties of alcohols. We learned that the structure of alcohols controls the properties of various alcohols. So we would continue the discussions from where we left. We learned that the alcohols are those which are normally called, if they represent something of this size, this sort, if the double bond is substituted with a hydroxy group, or if the hydroxy group is attached to sp2 carbon, they are called phenols in this case, and they're also called enols if you have sp2 carbon containing hydroxy group. Okay. So depending upon the types of alcohols, there are various methods to make them. One of the methods that we looked into was the reduction of carbonyl compounds using sodium borohydride or lithium aluminum hydride and carbonyl compounds. Depending upon the type of carbonyl compounds, you can expect different types of alcohols to be formed upon reduction. Okay, this Y could be different substituent. If you have ketone, we can make secondary alcohols out of the reduction of carbonyl compound, which is a ketone. Rest of the carbonyl compounds such as esters, aldehydes, acid chlorides, acids, they result in primary alcohol. Amides, upon reduction, some of the reducing agents do convert them into alcohols, but most of the reducing agents convert amides into amines. Amines are formed from reduction of amides. Primary alcohols are formed from the rest of the functional groups, and the ketones give secondary alcohols upon reduction of the carbonyl group. And there is another functional group that we would come across, that is reduction of nitriles. There is also a carbonyl derivative, but that also leads to a reduction of nitrile group into an amine. So except for these two functional groups, I think most of the other functional groups result in alcohols, but many of them result in primary alcohols because we are adding hydride, and hydride is what is making the bond, right? So the question is, how can we make a higher homolog than what we can make from this carbonyl compound? Let's say we want to add a side chain that has more number of carbons than hydrogen itself. So how do we make secondary alcohols from carbonyl compounds is the discussion of today's lecture. So let's start from that point. So the scientist who came up with the method of making higher alcohols from a lower homolog is Grignard. So this reaction is named after Grignard. Victor Grignard got Nobel Prize for this reaction, so you can appreciate the efforts that he has spent and the utility of this method in organic synthesis. That's the reason why this is called Grignard reaction. Okay, and I'm sure some of you did this reaction in the labs. It's the very reaction that we use in synthesis as well, in synthesis of medically important compounds. What are Grignard reagents? How do they work? What do they result into? That's the essence of today's lecture. Grignard reagents are normally the magnesium compounds. These are called alkyl magnesium compounds or organomagnesium compounds, depending upon the group that is attached to magnesium. And it could be anything, iodide, halide, or bromide, etc. So depending upon the nature of the alkyl group, depending upon the halide, the reactivity of magnesium compounds would differ. For example, here the electron density is polarized towards the alkyl halide, and as a result R is delta positive and X is delta negative. So what Grignard did is he inserted magnesium between R and X to make Grignard reagent, which is comprised of magnesium attached to carbon, and as a result the magnesium is electropositive and the electrons are pushed towards R group. So R in here is equivalent to R minus, right? So we had an R plus here, and we had R plus here, sorry about it, and now we have R minus. So what did he do? He employed magnesium and he reversed the polarity of the R group, or in other words, he reversed the polarity of carbon from carbon plus to carbon minus. Okay, so this was an electrophilic carbon. Now he converted that very carbon into nucleophilic carbon. This reversal of polarity is called Ampoulant. So it doesn't have to be magnesium, it can be any organometallic species. So M denotes that. M could be any metal. Depending upon the valency of the metal, depending upon the alkyl halide, the reactivity will be different, the number of R groups will be different, so on and so forth. So what is the essence of this reaction is that you have an organometallic reagent that is equivalent to carbon ion, and they act as powerful nucleophiles and bases. When do we call something a nucleophile and when do we call some species as a base? We call them nucleophiles if they donate their electrons to anything other than H+. If they donate electrons to H, then they are called bases. Okay? If they donate electrons to any other electrophiles other than H+, you can safely call them as nucleophiles. So there is subtle difference here. Most of the nucleophiles are bases, most of the bases are nucleophiles. So you don't have to be overly cautious about terminology here. But nevertheless, what you should understand that if you have water anywhere or any protic solvents in the reactions, for example methanol, you would not get what you want from a nucleophilic addition or actual Grignard reaction. What you would get is quenched product. It picks up the proton, so it accepts the proton from these species. That's why they are called bases, and they would result in alkane. For example, that's what is shown here. Alkyl magnesium halide here is accepting a proton. The proton source could be any protic solvents or acids, and they give you alkane. That's also a sort of Grignard reaction, but here Grignard reagent is acting as a base, so that's the difference. So you got to be careful when you want to add them as a nucleophiles. You need to be doing them in non-protic solvents. If you carry out the reactions in protic solvents, you would get simple alkanes. Alkanes are of not much use because there is no functional group, right? Or you just get simple compounds rather than the alcohols. In this chapter we are focusing on alcohols, so we should be making sure that there is no acidic proton around. There is no water, there should not be any methanol, things like that. Okay. Anyhow, so here is an alcohol. We are trying to make this alcohol, and this is the carbonyl compound you have. If you notice, this carbonyl compound is only made up of one carbon. If you were to reduce this to sodium borohydride, you would only get methanol out of it, right? If at all, if sodium borohydride reduces, you would have got methanol out of it because it has one carbon and this has one carbon. So the reduction would have got you only so far. But if you wanted to make this alcohol out of this aldehyde, you got to think of as to how do you add this part of the product. So that has to come from some reagent. That reagent is Grignard reagent, and here this carbon is R minus now, in the sense that is negatively charged. That's your R minus is cyclohexyl minus and magnesium bromide. So if this here you have R minus and this is electropositive, we will talk about more of this carbonyl features when we get to the carbonyl compounds. Here we are just using them as synthones for making alcohols. So our focus is on the product in this chapter, that is alcohol, than the the aldehydes or ketones. So this is an electrophilic carbon, this is a nucleophilic carbon, and that's adding to an sp2 carbon, and the electrons polarize onto the oxygen, and when you add water, that alkoxide, whatever is that's formed, it gives you the product. So there are three things here that are required for successful synthesis of alcohols. The Grignard reagent, which in turn comes from alkyl halide. Let's say in this case it's bromide, and you treat that with magnesium, you get magnesium bromide. That magnesium bromide is reacted with formaldehyde in this case, and you get this cyclohexyl methanol. And there are three things as we talked about: alkyl magnesium bromide, formaldehyde, and the source of proton. Otherwise you would have got just O minus and whatever the magnesium plus bromide. So that's an alkoxide, right? So in order to quench that alkoxide, you need to add water, and this is called workup. All the reactions normally need some or the other form of workup. Some reactions need acid workup, some reactions need basic workup, but these Grignard reactions are quenched with either ammonium chloride, or that's weak acid, you can say, or dilute hydrochloric acid. So that supplies the proton to the alkoxide, and that donates the proton. Okay, so that is a typical Grignard reaction. You have a Grignard reagent, you have a carbonyl compound, and you have water at the end of the reaction to quench the alkoxide, and you get alcohols. So can we write the products of different aldehydes that we see here? So this is an aldehyde, but this aldehyde has an alkyl group, and we are adding another group. Here we have a phenyl magnesium bromide, so we can now make alcohols that are substituted with aromatic rings. Right? Notice that this alcohol is on the aliphatic carbon, not on, sorry, it's on the sp3 carbon, not on this sp2 carbon. So this cannot be called as phenol, right? This is simply called the secondary alcohols, right? Okay, because it has two alkyl groups. And if you have a ketone, you get another alkyl group from this or magnesium bromide, and you already had two R groups attached to carbonyl, so that would result in the formation of a tertiary alcohol. So let's summarize the discussion that we had so far. If you react a Grignard reagent with an aldehyde, you get primary alcohol. If you react a Grignard reagent with a ketone, you get tertiary alcohols. So depending upon the type of alcohol you want, you can choose the carbonyl compound. If you have formaldehyde, you get primary alcohols. So if that's the only aldehyde that can give primary alcohols. Rest of the aldehydes give you secondary alcohols. Ketones give you tertiary alcohols. So I can make all sorts of alcohols if I have Grignard reagents that I want to attach. Okay. So there are some examples for your benefit. Try and solve them. I would try to solve something that's more complex. What would happen if it's an ester, right? So we talked about formaldehyde, we talked about some aldehyde here, that's 3-methylbutanol, we talked about ketone, but what would be the product of an ester out of Grignard reaction, right? That's something we'll look into. So this is the summary of what we discussed. And now instead of showing a specific alkyl magnesium bromide, the very discussion has been generalized in a generic form. Formaldehydes result in the primary alcohol because the carbonyl has two hydrogens, and those hydrogens are retained. If carbon's valency is satisfied by two hydrogens and some other groups, then that can be regarded as primary alcohol. Sorry, yep, that's primary alcohol. This is a typo. And the secondary alcohols are derived from the addition of R minus magnesium bromide to aldehydes, anything that has an R group, which is other than a hydrogen. If you have hydrogens, you get primary alcohols. If you have an R group, one hydrogen, you get secondary alcohols. Okay, that carbon is secondary carbon. Tertiary alcohols are derived from addition of Grignard reagents to the carbonyl of ketones, and as a result you get tertiary alcohols. If we have an ester, you can make a quaternary alcohol. How is it possible? Let's look into the mechanism in a minute. That would be clear to you. Okay, so anyhow, sorry, this is also a tertiary alcohol. There cannot be a quaternary alcohol. Quaternary alcohol is something that has 4 R groups. If a carbon has 4 R groups, its valency is already satisfied, so you cannot have another hydroxy group for that, and that's not a valid structure, right? There's pentavalent carbon, and pentavalent carbons do not exist. Okay, you're breaking the valency rule. So anyhow, so any questions? If not, let's move forward, and we will look into the mechanism of the addition of Grignard reagent to the ester. It's same as the reduction of esters. There are 2 stages. One is the first step is addition of 1 equivalent of Grignard reagent to this ester. This is a carbonyl one. Again, let's do the mechanism of a carbonyl of a ketone. And as a result, these electrons are moved onto the oxygen, and that forms an alkoxide. This is called alkoxide. Magnesium alkoxide, because this is magnesium. Then we need to add water. Water gives the proton. In other words, this attacks the proton, and that in turn goes to the hydroxy, and that hydroxy group comes back and finds magnesium. So you will get as a result magnesium hydroxide as a byproduct, right? And the product is addition product across the pi bond. So you had a pi bond. This was a pi bond. You added R minus on one end. You added H plus on the other end. So essentially, it's giving a secondary alcohol, tertiary alcohol. The carbonyl compounds that are ketones would give you tertiary alcohols. This is the same mechanism, so I'm going to skip it. Or magnesium bromide that we have, or our Grignard reagent, could be anything, as long as it has a side chain that's enough. It could be aromatic, it could be aliphatic, it could be unsaturated, whatever it is. And these R groups are also kind of not that critical. It could be any of those. As long as sterically it's not hindered, then the carbonyl can be approached by the Grignard reagent, and it results into tertiary alcohols. So that's what we talked about. Can you write the mechanism for aldehyde reduction? You just replace this R2 with one hydrogen, that's an aldehyde. So your product has hydrogen where R2 was, and as a result you get a secondary alcohol from aldehydes. Okay, so the mechanism remains same. So that's why I tell you that you keep focusing on the reacting partners, that is R minus here, that even CH2, whatever the carbon, and then some R group, and that's a nucleophile and this electrophile. That's all it matters. The spectators are not that important. They do control the reactivities, but they cannot change the course of the reaction or the path of the reaction. So the Grignard reactions of carbonyl compounds always result in alcohols, right? So let's look into the mechanism of the reduction of esters. The same thing, so I'm skipping. This is also the reduction of Grignard reaction of ketones. So you can make symmetrical alcohols where all the R groups are same, or they could be different. For example, this R group is different than these 2 R groups. I can make a Grignard reagent which is containing 3 different types of R groups, and I can start from any aldehyde or any ketone here and then add the third one. What do I mean by that? If I want to add R3, then I have to take these R2 as part of ketone. R1 and R2 are part of the carbonyl compound. These R groups can be either part of the carbonyl compound or they can be part of the Grignard reagent. So what should be the Grignard reagent? The Grignard reagent has to be the R3 group, right? So, or this very compound can be made from R3 containing carbonyl compound, and I would add now R1 containing magnesium. In other words, there are three ways to make this compound. That is adding Grignard reagent to the respective carbonyl compound. For example, if I want to make a tertiary phenol of this kind, and there is no reason to plan here much. There is not much planning here. You take benzophenol and add phenyl magnesium bromide. But if I had a methyl group here and an ethyl group here, then I need to plan as to what ketone do I take and what phenyl group, what Grignard reagent do I take. Okay. So then things would be different. You'll have to plan and see what is commercially available, what is not commercially available. We'll get to that when you practice some problems. Okay. So anyhow, this is an isopropyl bromide. You are making a Grignard reagent of isopropyl bromide using magnesium, and normally you use ethers as solvents in this reaction because they have coordination to magnesium because of the lone pairs on oxygen, and they stabilize the reagent that is formed. For example, this is dimethyl ether. It's very low boiling. Let's say diethyl ether. This is about coordination, right? So because of this lone pairs, ethers are good coordinating solvents, and they stabilize this reagent by coordinating with their oxygens. So that's not quite bonding, but just solvation. So when you add D2O, what would happen to this? This would be quenched by deuterium, right? This would add to D, and this would break the bond, and as a result you get a D there. And this is nothing but an alkane, just that it's an isotopic hydrogen that is been attached. So these are good for making deuterated compounds. In some cases we do need deuterated compounds, so deuterium can be introduced in the form of D2O. So order of the reactivity would be in this order. The water or alcohols or acid protons would definitely react violently with the Grignard reagent. That's why we need to avoid using any of these reagents if you don't want to have the alkanes. If you have any of these reagents, even if I had aldehyde suspended in water, the Grignard reagent would react with water than to react with aldehyde, because these are more reactive. So that's why we don't want water anywhere nearby when you want to do a Grignard reaction. So the next thing would be aldehyde, because it's not asterically hindered. Moreover, the delta positive charge is not decreased by the hydrogen. Otherwise, R group is an electron donating group. Alkyl groups are electron donating group through sigma, through hyperconjugation. So if you have two R groups, this delta positive is reduced and lowered. As a result, this is not as electrophilic as this carbon. So the aldehydes are faster or more reactive than ketones. How about esters? Esters are much sluggish because now you have an oxygen which can donate, which can participate in resonance, and that would donate the electrons to this carbon, and as a result this carbon is no longer delta positive because you are donating the electrons. So this goes off, and as a result R minus has to add here. So if there is no positive charge, then our negative charge would not find it. This is nucleophile, strong nucleophile, but you also need an electrophile, right? This is an electrophile. The reactivity of the electrophile depends on the charge density on the electrophilic carbon. That's the electrophilicity that goes down if you have electron donating groups. Okay, so that's the reason why esters are not as reactive as ketones and aldehydes. So this is the mechanism of ester reduction. This is giving a tertiary alcohol. Let's look into the mechanism. This is nucleophilic and this is electrophilic. So the electrons are flowing from nucleophile to electrophile, and this has to break a bond. Otherwise carbon would make 5 bonds, right? So whenever you make a bond to tetravalent carbon, you got to break a bond. And this happens in solvent ether, right? That's something you have to note. There's no water around, so this alkoxide waits for you to add water in the workup, and when you add the water, it would result in ketone. But even if you don't add water, what's happening here is this electron pair can go back, repolarize to the carbon, and as a result this becomes carbon double bond, and this OR is leaving group. Okay, and that forms a ketone. So probably you don't need water here as of now. So let's wait for the workup for some more time. Okay, there's no hurry to do the workup because there's no need of water here because there's no hydrogen here. See that? So it's forming a ketone, but ketone is reactive, and it's more reactive than ester, and as a result the R minus is adding to the ketone that is formed in the first step rather than adding to the ester. So the product itself is competing the reactant for Grignard reagent. This is a product of the first step, and this is the starting material, right? So though there is some starting material left, as soon as this product is formed, it competes for the R magnesium bromide, and then the magnesium bromide adds to the ketone, and as a result whatever the ketone is formed is just transient because it undergoes a faster reaction, and then it results in the addition of another R group because one more equivalent is reacting, and you get two R groups, one from the first reaction and the second one from the second addition, and finally now it cannot do anything even if these are not good leaving groups, so this stays in alkoxide form, and when you add water or acid it gets quenched to give you tertiary alcohols. Okay, that's why esters undergo double Grignard twice. In the same reaction, the two additions happening. So you can say two Grignard reactions are done in one pot. First addition leads to a ketone compound undergoes further addition to give you tertiary alcohol. Because there is a leaving group. If this is not a leaving group, this would just stay in the alkoxide form, right? But however, the O with oxide alkoxide can stabilize itself to some extent because oxygen is electronegative, so it's a good leaving group. So ketone is just an intermediate term that momentarily exists in the reaction pot. You cannot isolate ketone unless you have special conditions from a carbonyl compound that is like acid chloride or ester, because this is faster reacting than the starting material, so this undergoes quick addition again, second addition that results in tertiary alcohols. Okay, so that's something you have to remember, and we can use this method to make mixed alcohols where R1 and R2 could be different groups, but at least two R groups would be one and the same. So whenever you have an alcohol, if I ask you to make an alcohol which has two different groups, let's say you have that, so you identify the groups that have two similar groups, and if I ask you to identify as to what ester would you use, then just go for the odd alkyl group. These two are same. This is methyl, this is also methyl. So I would take an ester which is containing the same number of carbons, 1, 2, 3, 4, 5. So this carbon is coming from the carbonyl, so that has to be fifth carbon. 1, 2, 3, 4, 5, 6. So we don't need this carbon. Okay. So to this, because this is a leaving group, we don't want to count that. To this compound, if I add, this is retrosynthesis. So I'm planning my reaction as to what starting materials do I use, right? So this is planning retrosynthesis. In synthesis direction, I just have to add methyl magnesium bromide twice. Two equivalents of this methyl magnesium bromide would give me this alcohol. So this at least symmetric alcohol which has at least two similar groups can be synthesized through the reduction of esters. If you have three different groups, like for example, if I had an alcohol which is of this type, this is a tertiary alcohol, there are three R groups, but all the R groups are different from one another. This is a phenyl group, this is a methyl group, this is a propyl group, and as a result I cannot employ ester reduction or acid chloride reduction for that matter, because esters and aldehydes, esters and acid chlorides undergo two additions of the same Grignard reagent. As a result, you get two similar groups on the on the alcohol, but this has 3 different groups, so I cannot use this method. So there are limitations and there are advantages to this. So you got to know what you want to make from what you have. That's why there is the synthesis exercise for your benefit. So for example, I can make this out of ester reduction. So what would be my starting material? I would start off with something like this carbon, and this has to come from that, and this could be or magnesium bromide. I have phenyl magnesium bromide, and as a result I would take 2 equivalents of phenyl magnesium bromide in ether as a solvent, and that's the first step. And the second step, I would add water. So I'm adding one phenyl group first time, and then that forms a phenyl ketone, and that phenyl ketone undergoes second addition, that second equivalent of 2 equivalents, second equivalent of phenyl magnesium bromide to give me this alcohol. In here I have 2 methyl groups similar, so I would take the methyl magnesium bromide as a reagent of Grignard, okay, 2 equivalents, and then I take this ester which has 3 carbons, with 1, 2, 3. So those 3 carbons are say here, okay, and then you add 2 equivalents of methyl magnesium bromide, and then just all the reactions are accompanied by water quenching. Otherwise you would just get an alkoxide. So you got to show that you are quenching the reaction at the end of the reaction. So can you write the starting metals for all of these? Why not, right? So this I would rather make from an aldehyde or an aldehyde, because this is what secondary alcohol, right? So in the secondary alcohol case, you just take one side as an aldehyde. For example, I'll take this side as an aldehyde, and then this side would be alkyl magnesium bromide. That's ethyl group, so I would take ethyl magnesium bromide and then add ethyl magnesium bromide to aldehyde, and that becomes an alcohol. Or I could reverse the polarity. I can take this side as a side chain, and then the whole thing can be aldehyde. So then I need a propanaldehyde plus allyl magnesium bromide, because this is an allyl group, right? You have 3 carbons, so we need to make sure there are 3 carbons, and magnesium bromide, and now as a result I can make the very alcohol again. Which one is advantageous? Depending upon the needs, depending upon what you have in the lab, you can choose from one of them. If I had this aldehyde, I can use methyl magnesium bromide. If I had this aldehyde in my lab, I can use allyl magnesium bromide. I would prefer this method because this aldehyde is expensive even if it exists, right? This is kind of favored route. So you have to see, once you plan the reaction, and then you look into what is commercially available and then buy them to make the required compound. If you find that something is not commercially available, then you have to go back to Blackboard and plan it as per the commercial availability. That's what we do in real lab, but you would get credit for either way, either way you do on the paper. You can use this method, let's say method 1 or method 2. Why are there 2 methods? Because it's a secondary alcohol, there are 2 R groups. I can choose any R group as part of ketone or as part of Grignard reagent. So that's why you can have more than one correct answer here, right? So I'll let you solve some of these problems. If you have problems, then we can come back and discuss in the office hours or in the regular. What would happen if I have an epoxide? We'll talk about these epoxides, but just even if you don't know anything about this epoxide, you can regard this as a cyclic ether, right? This cyclic ether, because it has oxygen and it has lone pairs, it has 2 lone pairs, and the electrons are polarized towards oxygen, because oxygen is more electronegative. So oxygen has a delta negative charge, and these groups have delta positive charge. So where would Grignard reagent attack? Grignard reagent would prefer to attack at the carbon than at the oxygen. Which carbon? Both the carbons are symmetrical here. When the asymmetry comes in, for example, this is symmetrical epoxide, so it doesn't matter whether it attacks this position or this position. But when you have asymmetrical, like no symmetry here, right? This position is less hindered than this position, and then you have to pick one of the 2 positions, or the Grignard reagent would probably go to the less hindered position, and as a result you get a different type of product. Okay, but here it's symmetrical, so either it attacks here or here, it doesn't matter. But in this case, if it attacks here, then you get a different product than if it were to attack at a less hindered carbon. So when you have substituted epoxides, you need to be careful. When you have just simple epoxide, you can attack either side, so the product would be one and the same. So here the R minus is attacking the epoxide carbon, and as a result this bond is breaking to the oxygen, and the electrons are on the oxygen. So this is the bond that where R group attacked, right? So that's the new bond that you formed, and you had two carbons, and as a result this oxygen took off and it is now attached to only one carbon, that is second carbon here, and that's the reason why you get homologated alcohol rather than simple alcohol. So whenever you want to have this kind of alcohols which are extended by one more carbon, you cannot just use a formaldehyde. If you use a formaldehyde equivalent, you would have got a primary alcohol, but that primary alcohol would have been one carbon short. You wanted two carbons from your Grignard reagent, you had a Grignard reagent, and you wanted to add two methylene groups in between your hydroxy and the R group, then you got to think of epoxide. If there is only one CH2 that I need to add, then I think of formaldehyde. Okay, so depending upon the requirements, you choose your carbonyl compound. If I had an R group here, let's say R prime, then I have to think of an R prime in my aldehyde. So I need to have aldehyde that is other than formaldehyde. So let's do some example. You have methyl magnesium iodide and you have an epoxide, so you get a methyl, and two methylenes are coming from epoxide, so you make propyl alcohol out of epoxide and out of this ethylene oxide plus methyl magnesium bromide. So what are we doing here? We are homologating the chain by two carbons. And if you have substituted carbon, as I said, this phenyl group is bulky, so this phenyl group would not like to attack this carbon. It would rather go to this carbon, and as a result, you would get phenyl group here. That's a new carbon-carbon bond, and this oxygen is polarized into an alcohol. When you add water, it gets the proton. So any questions? Can we write the products of these reagents here? Let's try. This is the carbonyl compound. That's the carbonyl compound here. That's the carbonyl compound. Once you know the mechanism, once you know the principle, you can draw the products. I'll help you with that in a minute. Let's get to this. Some examples of ester. We already did this. So here it's reinforcing the concept that you learned. This is cyclic epoxide. That is cyclic ether. That is ethylene oxide, lactone, and an ester. What you have to notice is lactone is a sort of ester, so you got to learn that two equivalents of phenyl magnesium bromide will be added to the lactone. Okay, so for example, first equivalent would add, and as a result you still have the oxygen, but this oxygen is polarized. Let's add phenyl group to this one. These electrons are polarized onto the oxygen, that's why I put this as a phenoxide. This phenoxide would undergo repolarization, so that would come back, and as a result that carbon has to break one bond. So it would go to something of this ketone salt, right? So you open this oxygen, that's open, this bond is breaking, so that is alcohol. Okay, and now this ketone has, so it's not quite an alcohol, it's still phenoxide because we haven't added water. Proton has come back. So you add another phenyl magnesium bromide, another equivalent of phenyl magnesium bromide. So whenever you do these reactions of esters and lactones and these oxidized carbonyl compounds, you use two equivalents of Grignard reagent. Okay, so by default you have to use that. Otherwise you will get mixtures of products, so you don't want to have that. So if you use two equivalents, you can push this all the way to the completion, and you get O minus and O minus here. And when you add water, that gets quenched, and to result in phenol of this kind. So with the epoxide, you would get the same thing like what we did before. That's adding there, and this is going on to the oxygen. as a result you get two carbons inserted between the R group and the hydroxy. Okay, so you got to look at what is given to you, what is the starting material and what is the reagent, and then thereby you can predict the product. Or if you are given the product, you can predict the reagents. Sometimes we give both the two reagents and ask you to find the product. Sometimes we give you one reagent and one reagent and one product, and then ask you to find the other reagent. So the questions can come in any form. What is expected of you is to know the mechanism of the reaction, so that you can attempt any sort of questions that's thrown at you. So let's take an example here again. This is phenyl magnesium bromide. What is the reaction of that? This is also phenyl magnesium bromide. What would be the reaction? You have a carbonyl compound which is a ketone as well as an ester, and there are some acidic protons here. Whether that would be surviving that reaction, we don't know that. So you got to look up that kind of reactions. And this is a lactone. And this is where the products are given and you are asked to synthesize. Each of these products can be made more than one way, so that's why we have three arrows. So you got to find out those things. Okay. There are more synthesis problems here. So let's do some of these things. I would like to say that this would pick up this proton, which is an active methylene. We'll learn in chapter 19, and that would get quenched to kind of a benzene kind of a ring, because phenyl picks up the proton. Here it's acting like a base, and as a result the base is picking up the proton. That means phenyl group R minus is picking the hydrogen. You get the product like that. Or if this were to act as a nucleophile, this phenyl group would attack the carbonyl ketone first, and then would it attack the esters later on. Then as a result it would make more substituted alcohols. But I would like to think that this does not happen, because this hydrogen is acidic hydrogen, and that can be picked up by the base, because we pick up that hydrogen which is flanked by two carbonyls is called an active methylene hydrogen, and that active methylene hydrogen is very active, so that would act as an electrophilic hydrogen. So that acidic hydrogen, and that quenches the Grignard reagent and you get benzene. What would happen if I had a phenyl magnesium bromide like this, to an alcohol which is containing an ester? True, it has an ester, but it does have an alcohol, and we saw that protic solvents react faster than esters or aldehydes react, because they are stronger bases than stronger nucleophiles, right? So this would act as a base and pick up the hydrogen, and it would lead to the same product, that is benzene. In this case it's abstracting the hydrogen, right? So it's acting as a base. So if you don't have that kind of acidic protons, then for example this is a carbonyl compound which is a ketone, and you have ethyl bromide here, ethyl magnesium bromide, and that's adding to that, and it goes to oxygen and becomes oxide, and that gets quenched, and as a result you have an alcohol. This is the quenching state. You get ethyl group, and you also have a methyl group. So I am retaining whatever is attached to this carbon in the form of phenyl and methyl, and I am adding this ethyl to that, so you get tertiary alcohols. So you got to be able to write the products and the mechanisms of these reactions. And this is an acetone, and this is a Grignard reagent. So you got to draw the acetone structure out, and then add this Grignard reagent to that, and that's acetone structure, and that's electrophilic carbon, and that alcohols are polarized, so that hydroxy group is polarized in that fashion. So I'm going to retain the two of these methyls and attached to the acetone, and then that's the methyl group. I just messed up with that. That's the tertiary alcohol, because it's a ketone and a Grignard reagent, right? And here is an example where you have a bromide, and you have to look at the reagents. What would happen in the first step? It would form a Grignard reagent. Second step is adding one carbon, and that's a formaldehyde. So you get CH2OH. We had three carbons in the reagent, so those three carbons are retained, and this is a carbon of formaldehyde. That's why I've drawn it differently, and you get primary alcohol. Okay, so what would be the product of this lactone here? The lactones would give tertiary alcohols, and they also would open up. So you get whatever the Grignard reagent that we have. That side it opens up. On ether side and the alcohol side, it opens up into an alcohol. The end of the reaction. So that's the carbon, the where the oxygen is attached. So the reaction actually happens at that carbonyl carbon, and that's where two methyl groups would be added. If there are no equivalents specified, whenever you have esters, you imagine that there are two equivalents of methyl magnesium bromide, and that's the carbon of lactone, and that's where two equivalents of this would be added, and that's an alcohol. So there are two oxygens would be retained in the product as well here, because though it's a leaving group, that leaving group is attached to the molecule, so it quite doesn't go away. So you get a diol, okay? And with this epoxide, you get ring opened 2 carbon containing primary alcohol. And these are synthesis problems. So let me wipe this off. The eraser is not working for some reason. So anyhow, so whenever you have a synthesis problem, let's solve some of these synthesis problems. I'll let you solve these problems. I'll solve this for you. You got to see what is given to you, and then you have to, sorry about the disturbance here. Then you have to subtract this part from the product, so that's gone. So what is required? You need this aldehyde. Whatever is left comes as an aldehyde. For example, that is what you need to add. Once you subtract the reagent from the product, you know what is missing, and that missing part has to come in the form of carbonyl, and this is not quite Grignard. So first step would be to make the Grignard. So you have to have magnesium and ether to make the Grignard. Second step, you add the aldehyde. Third step, you add water. So that's what you did here. You synthesize this compound. There is not much choice here. You have to use this aldehyde because this is a secondary alcohol, right? If it were to be some other alcohol, you had other choices. So you're only bound to be struck with this alcohol. For only one answer exists for this. So how do I make this compound from the alkene? Alkene we haven't covered in this chapter, right? So where does this alkene come from? It can come from anywhere. We don't care. That's all you have. You have an alkene, and you need to get to this point. This is your starting point, and this is your product. That's why these are called synthesis problem. Propose a synthetic route. So it doesn't mean that one arrow doesn't mean that there's only one step. Here there's only one arrow, but we had 3 steps. Same is true here. Can I think of a way to convert this into something that I need here? How many carbons does it have? 1, 2, 3, 4. So the 4 group, 1, 2, 3, 4. If I can convert this 4 carbon containing compound somehow into an aldehyde or a ketone, I can or alkyl halide, I can use it, right? If I can convert this into an alkyl halide, I can use it for making Grignard reagent out of it and then add it. So how do I make an alkyl halide out of it? I need to add a bromide to that. So there is no selective way to add just bromide. If I add HBr, the HBr would go in Markovnikov way. I would get a secondary bromide. So I don't want to get a secondary bromide. I need a primary bromide because that's what we need here, 4 carbons, and this is a terminal carbon. So can I convert this into an alcohol using Markovnikov boration? So first type I would use hydroboration, BH3 or B2H6, and all the quenching reagents that we use, sodium hydroxide, whatever you want to use, and then you get the primary alcohol. And this primary alcohol can be converted into either aldehyde, or it can be converted into alkyl halide. by treating with HCl. So let's say if I treat that with HCl, this is my first step, this is my second step, right? So as a result I can get chloride out of it. If I have chloride, I can convert that into magnesium chloride by treating with magnesium in ether, right? So I can make Grignard reagent out of it, and then this piece can come from that. So the rest would be to worry about how to get this piece, and that can come in the form of ketone. There are quite a few things here that are troubling. We have to do the synthesis in a separate page. Okay, anyhow, I'll stop at this point and then I'll make one more presentation of synthesis problems. Thank you. Or we will do this in the class tomorrow.